Okay, without going through the details of the integration, which are very straightforward, we let u equal this, so that du equals delta v naught times d tau, okay? And then when we end up with the antiderivative, we're going to end up with the delta v naught in the denominator, which we'd better have, because if we take the derivative of this, we're going to get a delta v naught from the chain rule, and this will take care of it, leaving us mv naught times this. Okay, now if we'd have a tau here for our antiderivative, I've already done the substitution, upper limit t, lower limit 0. So the t goes in here for our upper limit, and then we subtract the lower limit. Well, tau would be 0 here. We substitute 0 for the tau that we get for our antiderivative, and we just get an m. Of course, it'd be an mv naught over m, but you know, this has been factored out. So we get this. And this equals what? Well, first of all, mv naught over delta v naught is just m over delta. And then it's times the natural log of the absolute value of m plus delta v naught t over m.
Oh. Natural log minus natural
Okay.
log is natural log of beta.
Now our units work out because units here are units of mass, as we checked out here, and the units of mass are, of course, units of mass. So we have a unitless quantity, and if we're going to do a natural log, we have to have a unitless quantity, and this is something we want to keep in mind. If we always check out our dimensions and our units, we get used to this idea. If we don't, we don't. And then our spacecraft crashes into Mars, and for carrying people, that's even worse. Okay? So even if we avoid substituting using pounds where we mean newtons or kilograms, even worse, we still have a disaster on our hands. Okay, so there's our position function. Now, how is that going to work with our given initial conditions? Because we have to make some assumptions that are going to have a big effect on our final result.